The Industrial Revolution in the 18th century was a huge catalyst for the industrial manufacturing industry, bringing with it many innovations to the industry. Among these innovations was the use of machinery for the production of other machines. The upsurge of industrial manufacturing emboldened firms to introduce more technology in order to serve certain purposes, such as the transmission of power, generation of electricity, and correction of distortions in astronomical seeing, or simply tackle contemporary issues, specifically natural disasters. With this notion in mind, one may question, what are the basic principles behind the industry? The answer is primarily hinged upon waves and optics. In physics, wave optics is the branch of optics which studies reflection, refraction, dispersion, interference, diffraction, polarization, and other phenomena. These explain how and why the industry chooses to manufacture certain machines, or how and why these machines behave the way they do. First, the field of applied science is concerned with the design and application of optical fibers. This is known as fiber optics. What are optical fibers for?
I'm only hearing optical fibers with the DSL lines. Not familiar with it.
Optical fibers, bright glasses.
A particular use for this is the transmission of power. Optical fibers can be used to transmit power using a photovoltaic cell to convert the light into electricity. Optical fibers function through transmitting light along its axis by the process of total internal reflection. Aside from transmission of power, waves and optics can be applied to the generation of power, particularly in the utilization of solar cells.
Do solar panels absorb the sun's heat?
Yes, of course.
I think yes.
Yeah, of course. I think that's what they
Solar
need for,
cells do not make use of the sun's heat to produce electricity, but rather the light waves. Solar cells are made out of an N-type and P-type semiconductor material. Solar radiation with wavelengths collide with the semiconductor medium found in solar cells, and this radiation has ample energy to knock electrons from their weak bonds. As a result, an electric current is created. There are certain phenomena that are key tools for the trapping of light. The first is interference, a phenomenon whereby two or more EM waves existing at a point constructively or destructively add together to some degree at that point. Another is scattering, which is a result of EM waves bouncing off of objects by being absorbed and emitted. This phenomenon is dependent on the property of the material. In diffraction, EM waves bounce off of objects by being absorbed and constructively interfering in specific directions. Another phenomena, called plasmonics, is the result of EM waves being absorbed by numerous electrons of a metal, exciting an oscillating plasma. This dissipates energy through electron collisions and re-radiates an EM scattered wave. Another use of waves and optics in the field of industry is the correction of distortions in astronomical seeing, through the use of wavefront sensors and deformable mirrors. When light from a star or another astronomical object enters the Earth's atmosphere, atmospheric turbulence can distort and move the image in various ways. An adaptive optics system tries to correct these distortions, using a wavefront sensor which takes some of the astronomical light, a deformable mirror that lies in the optical path, and a computer that receives input from the detector. The wavefront sensor measures the distortions the atmosphere has introduced on the timescale of a few milliseconds.
Waves and optics are also particularly useful in the mitigation or detection of natural disasters, particularly through the use of a photonics chip, radar technology, and seismographs. A research published in Nature Physics highlighted the formation of rare energetic natural events such as rogue waves, large surface waves that develop spontaneously in deep water. The research therefore made it possible to generate and control nanoscale rogue waves through the creation of a planar photonic crystal chip. It generates ultra-fast and sub-wavelength nanoscale rogue waves and offers controllability over these rare events. The next is in the use of radar technology.
How does radar technology work?
As in radar?
Yeah.
I have no idea.
Radar works by sending out radio waves that reflect off particles in the atmosphere. By measuring the strength of the waves that return to the radar and how long the round trip takes, forecasters can see the location and intensity of precipitation. For example, the Doppler radar is a specialized radar that uses the Doppler effect to produce velocity data about objects at a distance. It does this by bouncing a microwave signal off a desired target and analyzing how the object's motion has altered the frequency of the returned signal. Lastly, seismographs are securely mounted to the surface of the Earth, so when the ground starts shaking, the instrument's case moves. A seismometer is a suspended mass inside the seismograph that remains still while the case around it moves with the ground shaking. This works electromagnetically through movements of the magnet relative to the case, which generates small electric signals in the numerous coils of fine wire that can be sent to a computer or recorded onto paper. Waves and optics are extensively applied in various branches of the industry, and these contribute to supreme advancements in modern-day appliances and technology. This field of applied science allows productive efforts to be maximized through the utilization of electromagnetic waves in order to address and improve solutions towards issues faced at present. Making use of varying tools through wave optics improves industrial conditions of energy resourcing, astronomy, disaster mitigation, and innumerable others. Thus, wave optics manifests abundant benefits to the industry and is conducive to its innovation and further evolution. Through this, a more dynamic and competent society, as well as a more advantageous way of living, is achieved.